just by watching it, by feel. And it only goes for 5 minutes. I got it set for a 5-minute turn off. So we're going to start talking about pedostatics today. This chalk doesn't look very good. I'm going to give you an overview of how pedostatics testing is done and what the most common ways to test are. And then we might look at some equations. And I'll try to talk you through the material of the books because every one of your test flights is going to use pedostatics. And at the test pilot school, all the test pilot schools are actually is a pedostatics test flight. So I'm going to give you an idea of what it was like for me at the military. The pedostatics test flight for the military is done in this airplane, my favorite airplane, T-38. I got about 700, almost 800 hours of this airplane. And by far my favorite aircraft ever made. So they're going to be losing it in a few years at the test pilot school and at the training bases. I don't know what they're going to replace it with. It won't be as much fun as this, for sure. So here's the problem. I need to know the actual airspeed, the pitot head pressure, and you notice, the first thing you notice is how far the boom is out ahead. It's far out ahead, so that I get into the free stream. Now a test aircraft will actually go another 2-3 times past that. It'll go another 2 or 3 times past that, and it'll have a beta gauge for seismic. It'll have beta gauge and an alpha gauge. So this is just a regular airplane, but even a regular one, you can see they put the statics way out there. It's going to measure the difference between the dynamic pressure and the static pressure to give you a total head pressure, which is called QC. Here's the problem. The static port, where it's located, should measure free stream static pressure. It almost never can do that. It can only do that, or Bernoulli, it can only do that at one velocity if you put the static port at a certain time. So if I was flying at a certain velocity and I looked at the air and static pressure measured by a static port location, the air would look something like this. And it would go to 0 right around here, right around between the engine and the wing. So that's where you're going to put the static port. That's why when you go out to an airplane, you see the static port's always in the same location. They don't, let's put it on top of the fuselage this time. Let's put it on the bottom. They always put it in your Cessna, your Archers, whatever, your small airplanes, your big airplanes, your airliners are always right about here. And that's because the air tends to go to 0 there at approach speed. It goes to 0 there for approach speed when you're flying. Otherwise, there's an error. We have to figure out what that error is. It's called position error. So of all the things I do today, the one thing I want you to remember is you need to compute the position error for your velocities if you're doing it. And I'm going to go through how that's done, and I'll give you an easy way to do it. So I have a handout for each group that contains the equations that I'm going to give out. So I only have a few handouts, so I'm going to hand these. Just take one for your group if you have your group, and I'll make you another one. If you're short one, email me, and I'm keeping one to email. The same thing here. I'm going to give out a position error chart. And what I'd like you to do is to take one for your group. And then, actually, I probably have enough for most everybody. But it's a position error chart, and this is going to make your pedostatics testing easy, relatively easy in the long run. Okay. So stall people, make sure you get a copy of that since you guys are. Make sure that the stall folks get at least one. They're briefing next week. They'll be the first ones to use it. Otherwise, I'll just email me. I'll make another copy for you. So we need to find out what the position error in velocity is based on where our static port is, and that depends on our velocity. Does that kind of make sense? It depends on angle of attack. The more angle of attack, the more slipstream I get, the more downwash I get, the more error that you'll get in your output reading that you have to take into account. So the position error maps into a delta velocity error and a delta altitude error in the cockpit. Now the cool thing is that what I want you to remember for the exam, for midterm or for the final exam, what I want you to remember is that since I'm only using one static port, the position error and altitude and the velocity error, the velocity position error and indicated airspeed are related. They're related by a formula. I don't know if it's in that formula I gave you, but I'm going to put the formula on the board that comes from this flight test book, which by Kimberly. He's in English. So I've read most of this book. It's not very good, but you can borrow it if you want to look at it. What it is a flight test engineer who's writes in a variety of topics, and he covers some topics really well and some topics not very well at all. And he does not do a very good job with pedostatics. The author that does a really good job on almost all topics is Sean Roberts on his light aircraft performance. So, and those you'll have available for you also. A lot of today's briefing will be out of that. The next best topic, actually it's even better, but it's long, is the Air Force test pilot notes. The Air Force School test pilot notes on pedostatics is excellent. And of course, that's what I learned. And then there's the Navy side. The Navy is equivalent, but I think the Air Force is the most thorough. Sean Roberts is the easiest, a nice combination between them. So what we're going to do is to go through what this flight looks like and how it worked, and I'll show you a little bit how it worked. But what you have to do is you have to figure out what your position error, your velocity error, or your altitude error is in the cockpit with 2992 set in the altimeter, because you have to be flying the standard day. So you have to have 2992 set in the cockpit, and then you're going to measure either your altitude error or your position error on the flight at all the velocities that the aircraft can attain, because you change your angle of attack every time you do that. Gear up, gear down at slow airspeeds. You got to do the flaps down, gear down, then at high speed. So we're given, when we're at test pilot school, we're given one flight to do this. You get one flight, about an hour. And almost everybody picks the tower flyby because it's the most fun and it's the most dangerous, right? So you can pick the pacer method where you fly with an airplane that has calibrated, and then as you're flying formation, you'll read off the numbers and you'll read off your error then, the difference between your error and what the pacer aircraft has, both for altitude and velocity. You can do that. That's very difficult to do, by the way, and you're dependent on the guy flying a nice steady formation in the lead. You can't be just kind of moving around. It's got to be kind of like a Thunderbird. Actually, when I fly pacer, it's in a T-37, T-38 aircraft, not the 837 aircraft. And before you can take readings, the pilot has to put his hands on his helmet. So the airplane has to be perfectly trimmed in formation. You put your hands on your helmet and then you read. If you can't do that, they won't let you take the data. So it's very difficult to do the pacer. We don't do that here, obviously. That's okay. But the tower flyby is cool. So the way the tower flyby works is you run down a line at the airport, towards the airport, and then the tower, an engineer is sitting at the tower. And if I looked at it this way, the engineer would be over here, and he knows this distance, then he measures the angle that you go by, and based on this distance and the angle he measures, he knows the height of the tower, so he knows the altitude you should be reading. You read off the altitude, and then he compares it, and then you can get your altitude error. And again, by formula, by the chart that I just gave you, you can get your velocity error from that altitude error. You see how that works? Very, very quick, very fast. And we had people do tower flyby here at Oceano. It was a lot of fun. We had our own airplane. Because then the other guys are all over the field. They're playing games, doing triangulation. It was a lot of fun. That was like 15 years ago. It was a lot of fun. We haven't done it since. That's the principle behind it. And so you have one flight, so you have to come in and you have to make passes. The first pass you'll make is usually slow flight, gear and flaps down, as slow as you can go, down the line. That's very difficult. Then you'll raise gear, and you raise flaps, then you'll start going, and do one maybe 200 knots, and then you'll do one at 250 knots, and then 300 knots. Then it gets fun, because up to 300 knots, the only difficult one you have with gear and flaps down. It's hard to hold the aircraft very steady. And believe me, you don't go by the tower with your hands on your head at 50 feet altitude at 300 knots. You don't do that. So you keep your hand on the stick, and the guy in the back sees how you're doing. Then you go 350 knots. Then you go to 400 knots. And now it's really fun. Because you got time, you're going over the housing area here. So you got to slow down over the housing area, 250. And then you have to accelerate from 250 to 400 knots. Anticipate this black line that's on the runway. And then be exactly stable at the altitude before you cross the tower. Hard to do at 400 knots. But then you do 450 knots. And not many guys can do the 450 knots. But it's sure fun to try. You just don't want to overshoot too much if you're headed towards the base at 450 knots, because things go past pretty quickly. Then you do 500 knots. That's as fast as this will go without going to afterburner. And that's a kick. I still remember my 500 knot run. It's total luck. I think I'm going to start my turn here. I'm going to start my, because you're 250 knots, so you're accelerating up to 500. You give yourself about 150 feet, maybe 200 feet altitude. You roll down, then you start accelerating again. Then you got to catch the power, so you got to know kind of where the power is. Then you roll out, and you hope to God you see the black line. That's how it works. If you see the black line, you got some chance to maneuver. You got about 15 seconds to maneuver on the black line before you go past the top. You don't even, you don't even know. Everything is just a blur. So, I think the Air Force guys snuck this out. Is the sound on?
Yeah.
Did I lose it? Well, anyway, it's just a lot of static. So here's the tower flyby guy, and he's flying over the housing area now.
I can't see it on the projector.
It's not.
Oh, hold on. Turn the light back on.
Your,
Light back on. Why did it not?
Pull it out, then plug it in again.
You got to click laptop on the box
Yeah.
behind you. Can you change it to simple?
No? There we go. There we go. Okay. So let me get before you let me get rid of that. Okay. Now we're good. So this is Edwards. He's coming off the housing area now. You can see the lake bed off in the distance. That little white one.
Can you make it bigger?
Oh, yeah.
Yeah, we're going
There we go. So this is where you get lucky, because the lake bed's coming up. It's over there in the right-hand corner, right center, and you know that you're going to be smoking down the lake bed.